Something is out there, something so extreme that space itself bends around it. Something so dense that time slows to a crawl just by being near it. Something where the laws of physics themselves break down. Not even light can escape it, and there are billions of them, scattered across every galaxy in the observable universe. Today we're going inside a black hole, and by the end of this video you will never look at the night sky the same way again. So what actually is a black hole? At its core, it's simpler than you think, and stranger than you can imagine. A black hole is a region of space where gravity has become so extreme that it forms an object so massive and so dense that its gravitational pull becomes effectively infinite. Think of space as a fabric, a three-dimensional sheet stretching across the entire universe. Normally, massive objects like stars and planets make small dips in that fabric. But a black hole doesn't make a dip. It punches a hole straight through and creates a gravitational well so deep that nothing that crosses its edge can ever return. But where do black holes come from? They are born from death, the largest, most violent deaths in the universe, specifically from the deaths of the most massive stars. And those stars begin their lives in places like this. Gravity bends light itself. Around a black hole, light no longer travels in straight lines. It curves, bends, and wraps around the object, creating the ghostly ring of light you see here. This is the most powerful gravitational force in the cosmos. Concentrated. The most massive stars in the universe live fast and die violently. A star 20 times the mass of our Sun burns through its hydrogen fuel in just a few million years. For most of a star's life, two forces are in balance: the outward pressure of nuclear fusion, pushing out, and gravity, crushing in. The star exists in a state of constant, furious equilibrium. When it runs out of fuel, everything changes. The core begins to collapse. Within milliseconds, the iron core, which can no longer support nuclear fusion, begins falling inward under its own gravity. The collapse accelerates. The temperature spikes to hundreds of billions of degrees, crushing the core to the density of an atomic nucleus in less than a second. What remains is called a neutron star, one of the densest objects in the universe, a sphere barely 20 kilometers across, containing more mass than our Sun. But for the most massive stars, even that isn't enough to halt the collapse. The gravity is so extreme that even the neutrons are crushed. The collapse continues past all known physics, and a black hole is born. A black hole has three key structures, each more extreme than the last. The first and most famous is the event horizon. This is not a physical surface, it's a boundary, a mathematical point of no return in the fabric of space-time. Cross it, and nothing, no matter, no energy, no information, no light, can ever escape. Surrounding the event horizon is the accretion disk. As matter falls toward the black hole from nearby space, it doesn't fall straight in. It spirals, forming a flattened disk of superheated gas and dust, orbiting at a significant fraction of the speed of light. Friction in the disk heats the material to tens of millions of degrees, making the accretion disk one of the brightest, hottest regions in the known universe. Many black holes also produce two narrow, focused beams of energy and plasma, called relativistic jets, launched from the magnetic poles of the black hole system. These jets can extend for thousands, sometimes millions, of light years, and they are so powerful they are visible across billions of light years of space. And at the very center of everything, inside the event horizon, is the singularity, a point of theoretically infinite density, where the laws of physics as we know them cease to function. The singularity. Black holes don't just warp space, they warp time. The stronger the gravitational field, the slower time passes, a proven phenomenon called gravitational time dilation. Near a black hole, this effect becomes extreme. If you could hover just above the event horizon, without falling in, time for you would pass at a tiny fraction of the rate it passes for someone far away. An observer watching from a safe distance would see you slow down, and never quite arrive. And if you somehow survived the journey toward the event horizon, you would encounter tidal forces, the difference in gravitational pull between your head and your feet, even over a short distance, would be enormous. The gravitational gradient would stretch you vertically and compress you horizontally. stretched and compressed until nothing is recognizable. A process physicists call spaghettification. At exactly 1.5 times the radius of the event horizon, something remarkable happens to light. Light can orbit the black hole in a perfect circle, trapped in an unstable orbit. An eerie ring of photons circling forever at the boundary of escape. It's called the photon sphere, and it's one of the strangest places in the universe. Near the event horizon, space-time itself tilts. Physicists describe this using light cones, geometric shapes that define what futures are possible from any point. Far from a black hole, light cones are vertical, pointing in all directions of the future. Near the event horizon, they tilt inward, until at the horizon itself, the future only points in one direction, inward. If you're finding this as fascinating as we are, consider subscribing. We explore questions like this on the channel. Now, not all black holes are the same. There are at least 3 distinct categories, and they differ by size in ways that are almost impossible to comprehend. At the largest end, supermassive black holes. These are the behemoths at the centers of most galaxies, including our own Milky Way, ranging from millions to billions of solar masses. Our own galactic center harbors a supermassive black hole called Sagittarius A star, 4 million times the mass of our Sun. Then there are stellar mass black holes, the kind formed from dying stars, ranging from about 3 to 100 solar masses. These are the most common type, and the kind most likely to be found in binary star systems, feeding from the atmosphere of a companion star. And then there is a third, more mysterious category: primordial black holes, hypothetical objects that may have formed in the first moments after the Big Bang, from density fluctuations in the early universe. If they exist, they could range from microscopic to intermediate mass, possibly seeding the large-scale structure of the universe itself. For most of the history of physics, black holes were considered permanent, objects that would exist forever, growing larger as they consumed matter. Then, in 1974, Stephen Hawking proposed something revolutionary. Due to quantum mechanical effects near the event horizon, virtual particle pairs that form spontaneously in the quantum vacuum can be separated by the event horizon. One particle falls in, one escapes, and to conserve energy, the black hole loses a tiny amount of mass. This process is called Hawking radiation. It means black holes are not permanent. They slowly evaporate, radiating energy back into the universe over astronomical timescales. The smaller the black hole, the faster the evaporation. For a stellar mass black hole, this process would take longer than the current age of the universe. But here is the profound problem that Hawking radiation creates. When matter falls into a black hole, all information about it seems to be destroyed. But quantum mechanics says information cannot be destroyed. So where does the information go when the black hole evaporates? This is called the black hole information paradox, and it remains one of the deepest unsolved problems in theoretical physics. The largest known black hole is called TON 618. It contains 66 billion times the mass of our Sun. Its event horizon, the boundary of no return, is larger than our entire solar system. An object almost beyond human comprehension, and much closer to home. At the center of our own Milky Way galaxy sits Sagittarius A star, 4 million times the mass of our Sun. Astronomers have watched stars at the galactic center for decades, orbiting an invisible object 4 million times the mass of our Sun. In 2019, something extraordinary happened. A global network of radio telescopes called the Event Horizon Telescope pointed at the supermassive black hole at the center of the galaxy M87. And for the first time in the history of science, we had a picture. Black holes are regions where gravity has overcome every other force in nature. Born from the deaths of the most massive stars or seeded in the universe's first moments, containing an event horizon, an accretion disk, and at their center a singularity where physics ends. There are hundreds of billions of galaxies in the observable universe, and at the center of nearly every one, a supermassive black hole, silent and immense. Thank you so much for watching. We hope to see you again. Until next time.